Hi guys, this is my circuit, and today I'll be explaining how the stethoscope signal processing circuit works for the heartbeat acquisition system. Okay, so we'll be explaining our first part, which is home. So C1 is also a capacitor which will block DC signal and allow AC signal to pass. Okay. And for IC1A is a non-inverting preamplifier. So what does this circuit does is that it will amplify the signal. Okay, so we have a voltage divider here, which will divide our power supply, which we are going to connect later. So the power supply, we are giving it in 9 volts. So the voltage here will be 4.5 volts. This will cause the circuit to be running on a single supply mode. Okay, and from here we can calculate the passband gain, as we know what is R2, R3. So the passband gain is also 1 over R2 over R3, 1 plus R2 over R3, which is also equal to 1 plus 220k ohms over 10k ohms, which will give us 23. So the passband gain is 23. So from there, we can pull out our measurements, and we can see my maximum measurement for our higher gain is 21.57, which is close to our calculated passband gain. And so for all our measurement, we can plot the graph. We can plot our frequency response graph. So for our frequency response graph, from the peak, we can minus 3 dB down to figure out our FL and FH. So FL being frequency low and FH being frequency high. And so from there, we figure out that our FL is 14.6 Hz and our FH is 1500 Hz. So from there, we can figure out our bandwidth. Bandwidth is also equal to FH minus FL, which is 1500 Hz minus 14.6 Hz, which is also equal to 1485.4 Hz. Now, I'm going to explain how are we going to measure TP1 and TP2. So for TP1 is our input and TP2 is our output. So first we set our function generator, which is our signal input, to 1 kHz and 200 mV peak to peak. Then connect the probe of the function generator to TP1. Also, we'll be connecting our oscilloscope probe, one of our oscilloscope probe, to TP1 to measure the input. Then connect our other oscilloscope probe to TP2 to measure our output. This will be shown in the next video showing our measurements. For TP2 at 1 kHz 200 mV peak to peak, our voltage output is 3.48 volts. Okay. As for C4 is also have the same function as C1. It blocks DC and allows AC signal to pass. And so what is IC1B? IC1B, we have configured it to become a negative feedback loop amplifier, which will cause the signal to be 180 out of phase. Okay. So the trimmer will help us to will allow us to adjust the gain. And we also have a voltage divider, which also will act as a level shifter. So what is a level shifter? So since single supply mode will cause the negative side of the waveform to be cut. So a level shifter is required to shift the waveform up, causing the negative side to be waveform to be seen by us. As to measure TP3, our TP1, the function generator will be set to 1 kHz and 200 mV peak to peak. It's then connected to our TP1 here. Then the oscilloscope probe is also one of our oscilloscope probe is also connected to TP1 to measure input. Then our other oscilloscope probe will then be connected to TP3 to measure output. This is shown in the next video clip showing our measurements. For TP3, at 1 kHz 200 mV peak to peak, our voltage output is 5.44 volt. Okay, as for our IC2A, we have configured it to become a Ceylon key second order low pass filter. And so, it allows low frequency to pass and high frequency is blocked. So we can figure out our FC, which is 1 over 2 pi square root of R7 times R6 times C7 times C6, which will give us 995.925 Hz. And also, there's a voltage divider here, which will also act as a level shifter. As explained as just now, a level shifter will shift the waveform up, causing the negative side of the waveform to be seen. And there's also a capacitor here, C5, to block DC and allow AC signal to pass. Okay, so now let's look at our measurements. As you can see, our gain before 500 Hz, our gain is all 1, cause before 500 Hz is at unity gain, which is 1. But after 500 Hz, our gain starts decreasing. And from there, from our measurement, we can plot our frequency response curve. So from here, we can minus a 3 dB from the peak to find out our FL and FH. So our FC is also 900 Hz from where we plot. So 900 Hz minus our 0 Hz will give us back 900 Hz. So our bandwidth is 900 Hz. So from there we can backtrack to here, which are measured, which are calculated 995.925 Hz, which is somewhat the same. As for measuring TP4 test point 4, we will be using test point 3 as our input. We will be first setting our function generator to 5V VPP, 5V peak to peak, and measuring two different frequencies, 1 kHz and 200 Hz. And so, the same steps as measuring our 2 and 3, we will just be connecting oscilloscope and our function gen to TP3 and our other oscilloscope probe to TP4 to test for TP4 output. For TP4, at 200 Hz, 5V peak to peak, our voltage is 5.12 volt. But at 1 kHz, 5V V peak to peak, my voltage is 3.04 volt. As for LM386N-1, it's an audio amplifier which drives current to power speaker. So, it does not require a level shifter or voltage divider, as it is working as a single supply mode internally. Also, it's connected to C15, which is a capacitor to filter out the high frequency, stabilizing the output waveform. Also, there's a trimmer connected to it to adjust the gain. For our final test point 5, we'll be using TP1 as our input. So, we'll be testing two different frequencies, 1 kHz and 200 Hz at 200 mV peak to peak. So, the same procedure as our past test point, we'll be connecting the one oscillator and one function generator to TP1 to test, to give it its input signal and to measure the input signal. Also, the other oscillator probe is then connected to TP5 to test for its output signal. At TP5, 200 Hz, 200 mV V peak to peak, my voltage output is 5V. But when I set the frequency to 1 kHz, and at 200 mV peak to peak, my voltage output is 3.20 volt. And in the video, I have done the trimmer to show how it amplifies the circuit, how it amplifies the waveform. And once the waveform is amplified till saturation, the waveform is cut out.